Hi, this is Dr. Emanecker. We are going to continue looking at graphing with asymptotes, and we're going to look at some exponential functions here. First, I want to recall some of the information that was presented in an earlier video. There's actually a series of pieces of information you need to collect along the way. One of the first things you want to do is to verify what the domain is for both the function and for the derivative. I think I'll put a space in there so it's a little easier to read that that's a derivative. Then we want to need to compute the x and y intercepts and go on down the list. All right, so with this list in front of us, let's look at this function and we're going to consider graphing this. With the function y equals 3 plus e to the 0.4x, first notice the domain is all real numbers. There are no values of x that we could put into this that are going to cause any problems. We don't get any negatives in natural log. We don't get any negatives in a square root. We don't get zeros in denominators. It's all good. So the first step that we're going to consider is the domain. So the domain in this case is going to be x can be any real number we want it to be. So there's the first thing done. The second thing asks us to compute x and y intercepts. X-intercepts mean that y is 0. Well, to solve for the x-intercept here, what we're going to do is we're going to take our function, and we're going to substitute 0 in for y, and we're going to solve that. So that's going to give us 0 is equal to 3 plus e to the 0.4x. Subtract 3 from both sides, we get negative 3 is equal to e to the 0.4x. Then what we're going to do to cancel out the e is to apply its inverse, which is a natural log. And when we apply a natural log here, that's a problem. It's undefined. So what does that tell us about an x-intercept? There is no x-intercept. So whatever our graph is, it'll never run through the x-axis. Okay, so let's take a look at the y-intercepts. Actually, I'm going to put a box around this and a box around my domain. When I look at the y-intercept, to be on the y-axis, that means that x is equal to 0, which is going to give us y is equal to 3 plus e to the 0.4 times my x value is 0. Now be careful. This does not work out to be 3 because we have 3 plus e to the 0 is 1. So our y-intercept is going to be when x is 0 and y is 4. So if you want, we could go ahead and move to the graph on the far right side here and go 1, 2, 3, 4. I'm going to put that point in and I'm going to identify the coordinates of that is 0, 4. Okay, so we have the domain, the x-intercept, the y-intercept taken care of. Let's see what's next on the list. Okay, so we have our intercepts taken care of. So number 2 on the list is done. Number 3 on the list is to locate any asymptotes if they exist. Notice it says if they exist. It may be that there are no asymptotes. That's entirely possible. Okay, so for our asymptotes, I'm going to consider vertical asymptotes first. Vertical asymptotes occur where there is a 0 in the denominator or the function is undefined. Well, in this case, there are none. In fact, you can't get a 0 in a denominator. There isn't a denominator. Horizontal asymptotes are determined by looking at the limit as x goes to infinity of our function, which is going to be 3 plus e to the 0.4x. Okay, so as we evaluate this, what's going to wind up happening here is as we put larger and larger values in for x, this is just going to go to infinity. However, when we look at the limit as x approaches negative infinity of 3 plus e to the 0.4x, be careful because we're putting in large negative numbers. As we put in large negative numbers, that's going to be 1 over e to some huge power. 1 over some huge number is 0. This winds up equaling 3. Okay, this gives us a horizontal asymptote. Remember, horizontal asymptotes occur at y equals. Okay, so I'm going to go ahead and I'm going to insert a horizontal asymptote at y equals 3. So this asymptote's going to come through here, and I'm going to label this as y equals 3. And actually, at this point, you can probably pretty well guess what the graph is going to do because it has to flatten out on the y equals 3 as we move to the left. It has to go through that point 0, 4 as we cross the y-axis. And as the x values get large, the thing has to go to infinity. Okay, so we already have a pretty good idea that this graph is going to behave like that. Okay, but let's go ahead and let's make sure that we have everything all put together. And let's consider slant asymptotes. Slant asymptotes occur when you have a rational function and the numerator is 1 degree higher than the denominator. Well, we don't have a rational function here. Remember, a rational function is some kind of a polynomial divided by another polynomial. Slant asymptotes, none. Okay, locate where the function is increasing, decreasing, has critical values. To do this, I'm going to be looking for critical values. Critical values mean I want to determine where is the derivative 0. Well, y prime, the derivative of this function here, moving back up a little bit, is going to be the derivative of 3 is 0 plus. Then I need to take the derivative of e to the 0.4x. That's a chain rule. The derivative of e is going to give me back whatever I had, 0.4x. Then I take the derivative of the inside, which is just going to be 0.4. So I have 0.4 e to the 0.4x equals 0. Well, we could try to solve this. First, I would divide by 0.4, which is going to give me e to the 0.4x equals, when I divide by 0.4, the right-hand side is still 0. To solve for x, I need to apply natural log to both sides. And the catch here is, on this side, it does not exist. You cannot take the natural log of 0, which tells us then, as far as critical points go, there are none. There are no critical points here. Interesting. That means it doesn't turn around. That means that the slope never changes. In fact, on our graph, if we do this number line thing like what we're used to doing, and we evaluate the derivative of this, we can evaluate the derivative at any value we want to because they're all going to be on the same interval. Notice there are no breaks in the intervals because there are no places where the first derivative is 0. So I could make this simple, plug in 0. And if we evaluate the derivative at x equals 0, that means we're going to want to take this right here, plug 0 in for x, and it's going to give us 0.4 times e to the 0, which is 0.4 times 1 greater than 0. That means this function is always increasing. Well, that supports the graph that I proposed earlier. Let's continue on. Look for inflection points. Okay, so that means we need to use the second derivative. So in order to do the second derivative, I'm going to look for inflection points. The second derivative is equal to, now remember I'm taking the derivative of this, so it's going to give me 0.4. I'm going to have my e to the 0.4x, and then I multiply by 0.4. So the derivative is going to be 0.16 e to the 0.4x. And to get an inflection point, what we want to know is when does this equal 0? As with the first derivative, we can take and divide both sides by the 0.16, or the coefficient, whatever it may happen to be. The last time it was 0.4. The left-hand side will continue to be 0. Then when we try to apply the natural log to both sides, we're going to wind up in the same situation as we had with the first derivative, which tells us that there are no inflection points, none. It also allows us to evaluate our second derivative over the interval from negative infinity to infinity because there are no changes in the concavity. I can evaluate the second derivative at any value I want to. I'll make it something easy like 0. That means that I'm going to take 0 and substitute it in here, which will give me 0.16 times e to the 0 power, which is just 0.16 greater than 0. It's concave up. Well, if you take a look at the graph that we sketched, it is always increasing. It is always concave up. It's running asymptotic to the line y equals 3, and it does intersect the y-axis at 0, 4. There's your graph. Uh-oh, this one looks a little more challenging. We're going to go through the same steps as we did before. Okay, the first step is going to be our domain. The question is, are there any values of x where this 1 plus 30 e to the negative 0.2x equals 0? Remember, we're trying to determine if the denominator ever equals 0. Well, we can solve, and we're going to get 30 e to the negative 0.2x equals a negative 1. We can divide by the 30, and when we divide by 30, that's going to give us a negative 1 over 30. Then we take the natural log. And as we've seen in earlier cases, we run into troubles here. Okay? That's a math way of saying, uh-oh, we've got some troubles here. We have a contradiction. You cannot take the natural log of a negative number. What this says then is there are no places where the denominator equals 0. That means x can be any number you want it to be. There's our domain. Number 2, we're going to look for the x-intercept. Then we're going to look for the y-intercept. For the x-intercept, that means y is 0. Well, we just did that. Okay, we just did that when we were looking for the domain. Well, y equals 0, it's undefined. Undefined would be the denominator is 0, so we know that's not going to happen. But the question now is, can this function ever equal 0? Can we take 150 over 1 plus 30 e to the negative 0.2x and have that equal our y value of 0? Remember, we're setting y to 0. And the answer is no. The only way that a fraction can equal 0 is if the numerator is 0. That would mean 150 has to equal 0. Well, there's never a time when 150 equals 0, so x-intercept, there's none. This is never going to intersect the x-axis. That's kind of interesting. Okay, so what's going on next? The next thing we're going to do is we're going to take a look at the y-intercept. For the y-intercept, what we want to do is we want to recall that the y-intercept occurs where x is 0. So this is going to give us y is equal to 150, 1 plus 30 e to the negative 0.2 times 0. This is going to give us 150 over this is going to be 30 times e to the 0 power is 1. So we're going to have 30 times 1 is 30. Then we add the 1, 31. This is going to intersect the y-axis at 150 over 31, which, if you want to flip that into a fraction, gives us about 4.84, just to give us some idea of about where we are. So I'm going to, on the graph to the far right, come up 1, 2, 3, 4, 5, and right about there, I'm going to label this as an x value of 0 and a y value of 150 over 31, or a decimal approximation of 4.84. Important to label these because I doubt that you would look at that and just say, oh yeah, it's clear that the y value here is 4.84. So you need to label that. Okay, so we'll put a box around that. That's done. Okay, so we have our domain, we have our x and our y intercepts. Let's come back up here. We want to determine if there are any asymptotes. You can have them or you might not have them. So the next thing we're going to do, number 3 on the list, is asymptotes. First thing I'm going to look for is vertical asymptotes. Well, with a vertical asymptote, what's going to wind up being the case here is that's where the denominator is 0. Okay, remember, vertical asymptotes occur where the denominator equals 0. Does not exist. We've already talked about that. There are no vertical asymptotes. So let's talk about horizontal asymptotes. Horizontal asymptotes occur when we evaluate our function at either infinity or negative infinity. So what I'm going to do is I'm going to put y is equal to the limit as x approaches infinity, and I'm going to have my 150 over the 1 plus 30 e to the negative 0.2 x. Okay, so that gives us our first limit we need to evaluate. Okay, so if we think about putting bigger and bigger and bigger numbers in for x, we're going to have 150 in the numerator. In the denominator, we're going to have 1 plus 30. Then we're going to have e raised to. E is going to get to be a larger and larger exponent. So it's going to be like negative 100, negative 1,000, negative 1,000,000, negative 1,000,000,000. And what's going to happen is this whole piece here is going to go to 0. With that going to 0, that means that we have an asymptote. Really? We have an asymptote here at 150. Well, I'll move up to my graph. I'm kind of sad I put that 0, 4.8 right there. I'm going to need to move this down some because I'm going to need a lot more space on my graph. Okay, so I'm going to need to get up to 150 here. I'm going to do my 0. This is going to be the 0, 4 point, what was that, 84 right there. And I'm going to put in my horizontal asymptote like that. Okay, so there's one of them. One of them, because we still have a second limit to evaluate here. We need to also look at y is equal to the limit as x approaches negative infinity of our function, which is going to be this 150 over 1 plus 30 e to the negative 0.2x. And let's see what that gives us. Well, once again, we just need to think about what happens as the y values get bigger, or as the x values get bigger and bigger and bigger. As we plug more and more negative values into this exponent is always going to be positive because we're going to have the negative 0.2 times another negative number. So that's going to give us things like e to the 30th power, e to the 50th power. The denominator is going to get huge. And we're going to have 150 over a huge number. Eventually, this goes to 0. So we have a second asymptote here at 0. This is kind of interesting. We have an asymptote at y equals 150. We have an asymptote at y is equal to 0. Looks like our graph's going to be kind of trapped between those two asymptotes. Let's keep going and see what else we can figure out. Fourth thing on the list is to determine our critical values. Critical values occur where the derivative is 0. Okay, so I need to compute the derivative. Well, what this is going to give me here is the derivative is going to equal to, the denominator is pretty easy. It's 1 plus the 30 e to the negative 0.2x, that whole thing squared. Now, in the numerator, using the quotient rule, I'm going to have the derivative of the 150. So that's going to give me 0 times this 1 plus 30 e to the negative 0.2x minus, then I'm going to do the 150, and it's going to be times the derivative of the denominator. Well, the derivative of 1 is 0, and I have to take the derivative of this 30 e to the negative 0.2. It's going to give me 30 e to the negative 0.2x, and I'm going to wind up with I need a little more space there. I'm going to wind up with a negative 0.2 e to the negative 0.2x, like that. All right. From here, I can clean this up a bit. The denominator is going to be this 1 plus 30 e to the negative 0.2x squared. In the numerator, this whole first term is just 0 because it's times 0, so that goes away. In the second term, I have a negative times a negative, so that's going to be positive. Okay, so what I'm going to wind up with is I'm going to take the 0.2 times the 150. 0.2 times 150 is going to give me 30 times the 30 that we already have, so that's going to be 900 e to the negative 0.2x. Okay, critical values occur in two locations. The first of these is, where does the derivative equal 0? Well, the answer is never. The derivative never equals 0. That would mean that 900 times e to the negative 0.2x equals 0, but that never happens. The second thing is if my derivative is undefined. That would occur if the denominator is 0. Well, that never happens either. Wow, this is interesting. There are no critical values. This has no maxes, it has no mins. Interesting. If we go back up to our list, way up here, Number 6 on the list is locate where it's concave up and concave down. Okay, so that's the next thing to do. And before I do that, I want to come over to my graph. I'll draw a line here. And I'm going to put in my first derivative test. There are no critical values, so it's going to wind up being the same value for my derivative at any value of x. So I'll pick something simple like 0. Now remember, we have to evaluate the derivative at x equals 0. If I plug 0 in here and 0 in here, I'm going to wind up with 900 over, well, it's going to be 1 plus 30 squared. I don't really care what it is. I just need to know that it's bigger than 0. It's positive. Okay, so I can come over here. I can say, well, gosh, this is greater than 0, so it's always increasing. So we have a function that has to fit between those two asymptotes, and it's always increasing. Okay, let's keep going. We've already talked about needing to locate inflection points, which is where the second derivative is 0. Oh no. Okay, so 5 on the list is going to be inflection points. I'm saying oh no because we've in an earlier video went through one of these things where we had to do the derivative of a nasty looking derivative. We got to take the derivative of this. The second derivative is going to be equal to, now in the denominator it's going to be this 1 plus 30 e to the negative 0.2x squared squared. So that's going to be to the 4th power. So that's got that. In the numerator, we're going to take the derivative of this 900 e to the negative 0.2. I'm going to have a negative 0.2 times 900, which is going to give me 18. And a 0 e to the negative 0.2x times whatever's in the denominator. It's going to be this 1 plus 30 e to the negative 0.2x squared minus. Okay, so let's see here. If we take now the top function, which is going to be this 900 e to the negative 0.2x, and now we're going to multiply it times the derivative of the denominator. That's chain rule. We have 2 times this 1 plus 30 e to the negative 0.2x, and it'll be to the 1st power times the derivative of the inside. Well, the derivative of the inside, the derivative of 1 is 0. I'm going to have this 0.2 times 30, which is going to give me a negative 6 e to the negative 0.2x, like that. Okay, now I'm just looking over this to make sure I haven't made any negative sign mistakes. Sure don't want that happening. If I look at this first part, where I take the 900 times the negative 0.2, that should be a negative 180 e to the negative 0.2x. Okay, we have to solve this for 0. As we had done with an earlier one, I would suggest in this case to go after Wolfram alpha if you actually need to solve this. Okay, there actually is a location where this does equal 0. When I take this equation, I'm only going to take the numerator and substitute that into the Wolfram alpha because I want to know where this second derivative equals 0. Well, it equals 0 if the numerator is 0. The second thing we want to know is when is it undefined? It would be undefined when the denominator is equal to 0, but that never occurs. So the only place that we really need to concern ourselves with is where does the numerator equal 0? Definitely not an equation I would ask you to solve by hand, but I went on Wolfram Alpha, I entered it in, and came up with an x value right there. Okay, so it's 0.038. So we're going to call that our solution. Okay, and we get that the second derivative equals 0 at x equal to 0.038. I'll go check and make sure I copied that down correctly. Okay, yep. Okay, now for an inflection point, you need not only the x value, but you also need the y value for it to be a point. To get that, I'm going to come back to my original function. There it is. And I'm going to plug that in on the calculator and evaluate it. Okay, so go into the calculator. Notice I have already entered in the original function. Okay, so that I can go to the table and evaluate it. And at 0.038, we wind up with 4.87. We've seen a number like that. Now, my guess is, because I did some rounding with the function that was put into Wolfram Alpha, it's really trying to come up with 0, 4.8. This says the concavity changes at this location where it intersects the x-axis. Now, that means it's going to wind up with doing something like, it's going to be let me try that again. It's going to be concave down, concave up in order to get that to run along the asymptotes. You'll come up with something sort of like that. Wow, that's kind of a tricky problem to get through. The tricky part here is solving where the second derivative is 0. And very honestly, you could just go ahead and roughly sketch in something saying, you know what, it's got to come through here and it's going to do something like that, where it's got to go through that 0.04.84. Okay, because it's got to run asymptotic to both of those asymptotes. That's the only way to get the function to do that. Okay, whew. Let's take a look at something else. One last problem. This one's going to be a whole lot easier, I promise. Okay, we want to first consider, we're going through that list again. First thing we're going to do is the domain. For the domain, the question is what values of x are you allowed to use? Well, x can be negative, x can be positive. X is any number you want it to be. There's no place here that we're going to run into e to the x squared equals 0. It doesn't happen. Second thing, we want to do the x-intercept, and we want to do the y-intercept. With the x-intercept, this means that y is 0. Well, we've seen something like this before. We're going to have 0 equals e to the negative x squared. When you apply natural log to both sides to get rid of the e, we run into a problem here that can't be solved. Okay, x-intercept, never. Does not exist. Never goes through the x-axis. Y-intercept. The y-intercept means that x equals 0. So that's going to give us y equals e to the negative 0 squared, which is really just e to the 0, which is 1. This thing's going to intersect the y-axis at, let's try putting 1 there. The coordinates of this point are 0, 1. All right, Third thing on the list. What is the third thing on the list? Let's go all the way back up here. Here we go. Asymptotes, vertical, horizontal, and slant. Okay, first thing to notice, this is not a rational function where there's a polynomial in the numerator and a polynomial in the denominator. Translation, there is no slant asymptote. Let's take a look at vertical asymptotes. Okay, vertical asymptotes can occur where you get zeros in the denominator. Well, we've already talked about that. This is really 1 over e to the x squared. It's never 0. So vertical asymptotes, none. They never occur. Horizontal asymptotes. This is going to be the limit where x approaches infinity of e to the negative x squared. And we're also going to do the limit as x approaches negative infinity of e to the negative x squared. Now, when we put really big numbers in here and square them, they're going to get huge. But because of the negative, we're going to wind up with 1 over some huge number, which means that as x goes to infinity, the y value goes to 0. When we evaluate the limit as x goes to negative infinity, if we take a negative number, square it, we get a huge number. Okay, but it's going to be a huge positive number, which, because of the negative out front here, is then going to give us 1 over some huge number. Okay, which is once again going to take us to y equals 0. So whether you go to positive or negative infinity, you wind up with a horizontal asymptote. I'm putting it just a touch above the x-axis so you can actually see it there. We have an asymptote there at y equals 0. It's running along the x-axis, in other words. Okay. The third type of asymptote that we can consider is slant asymptotes, but there are none. We've already talked about why those don't occur. So there are none of those. On to step number 4, which is going to be our critical values. Notice there are a lot of steps to this, but you just take them one at a time and you can get through it. Okay, let's do the critical values. This is where the first derivative equals 0. The first derivative equals 0 means that we're going to have e to the negative x squared times the derivative of the exponent, which is going to be a negative 2x, equals 0. Okay, well, this we can handle. This means either e to the negative x squared equals 0 or a negative 2x equals 0, giving us x equals 0 as a critical value. We can display this as a critical point where x is 0 by evaluating our function way up here at the top, plugging in 0 for x. And when we plug in 0 for x, we get e to the 0, which isn't 0, it's 1. Interesting. We already have the point 0, 1 on the graph. Recall that was the y-intercept. It's also a critical point. We can go ahead and evaluate the first derivative while we're here. It's going to split at 0. So what I'm going to want to do here is I'm going to want to evaluate the first derivative at something negative. Okay, so if I put something negative in there, and like negative 1, square it, I get e to the negative 1. Well, that's greater than 0. Okay. Then if I take and evaluate the derivative at something like positive 1. And let's see here. My derivative is, remember, okay, when I put this negative 1 in, I'm evaluating it at the derivative. And the derivative is down here. So I put the negative 1 in there. That turns out being a positive number. Put the negative 1 in here. That turns out being a positive number. And a positive times a positive gives you a positive. However, on this side, I plug the 1 in here and the 1 in there. The e to the negative 1 power is positive. However, negative 2 times a positive 1 is negative. So I wind up on the right-hand side less than 0. So it says that the function is going to be increasing, then it's going to be decreasing. This also allows me to evaluate my critical point. Notice my critical point goes from increasing to decreasing, which means that this is going to be a max point. That's a maximum on the graph. Okay. Next thing we want to do is we want to locate inflection points. Okay. Inflection points occur where the second derivative is 0. In order to take the second derivative, what I want to do is I want to take the derivative of this negative 2x e to the negative x squared. That's a product rule. When I do the product rule, I'm going to get a negative 2 e to the negative x squared, the derivative of the negative 2x times e to the negative x squared, plus, then I'm going to have the 2x times the derivative of e to the negative x squared. That's a chain rule. With the derivative of e, just give me back what I started with. But the chain rule says to then take the derivative of the inside. So I have something like that. So what this is going to give us is 2e to the negative x squared minus 4x e to the negative x squared. And we have to solve this equal to 0. This can actually be done fairly handily with just algebra. What we're going to do here is we're going to factor out an e to the negative x squared from each term, which is going to leave us with 2 minus 4x. And one of these two factors, either e to the negative x squared equals 0, or is 2 minus 4x equals 0. When we solve the 2 minus 4x equals 0, we're going to wind up with, just checking everything, making sure it's all good here. Oh, this is going to be 2 minus 4x squared equals 0. Because see it, I have a 2x here, looking up here at the top of the screen. We have a 2x times a 2x, which is going to give us a 4x squared. Well, that'll change things a little bit. That's going to give us 2 equals 4x squared, where that gives us x squared is 1/2. If we take the square root, that gives us x is equal to 1 over the square root of 2. Multiply top and bottom by square root of 2, and we get square root of 2 over 2. But remember, when you take a square root, you get two values. You get plus and minus. So we do have two inflection points. We have an inflection point at negative square root of 2 over 2, and an inflection point of square root of 2 over 2. So that gives us our two x values. Now, to get the y values, I need to take and substitute this square root of 2 over 2 back into the original function. That's e to the negative x squared. In the first case, it's going to give me e to the negative, and I'm going to have a square root of 2 over 2 that's negative squared. Negative doesn't really make any difference inside because that's going to be gone. And what this is going to give me is e. Let's see, it's going to be 2 over 4. The negative on the outside will stay, and it's e to the negative 1/2. So there's that. When we evaluate square root 2 over 2, we wind up with the same thing. E negative 1 over 2, like that. Here are our two potential inflection points. What we need to do is come back up here for the second derivative. I want to put my negative square root 2 over 2 there. I'm going to erase this. And I'm going to put my square root 2 over 2 here. Okay, now, in order to determine concavity, oh, that's right, concave up or concave down, I'm going to take each of the two values and I'm going to put them into this. I would strongly encourage you to use the calculator for this. When you do this, if you pick a number that's to the left of negative square root of 2 over 2, for example, I'm going to pick the second derivative at negative 2. If you evaluate the second derivative at negative 2, it's going to turn out positive. If you evaluate the second derivative at 0, it's going to be negative, and the second derivative at something like 2 is going to be greater than 0. So with the second derivative evaluated at these three locations, it's going to give us concave up, concave down, and then concave up. In order to get my graph, I'm going to sketch out here. There's a panel here. Okay, see where the x equals 0 in the first derivative? That's going to be another line of demarcation. Then where the second derivative here, we've got something going there. So we have 1, 2, 3, 4 separate areas that we want to take a look at. And I'm going to do these one at a time. Okay. On the leftmost interval, it's increasing. Okay. Right here it says increasing and concave up. Increasing and concave up is going to look something like this. On the second interval, this area, it's still increasing, okay, and it is now no longer concave up, but it's now concave down. Okay, so it's going to wind up happening is it's still going up, but it's going up at a slowing rate. And remember, I've got to hit this maximum point of 0, 1. So this is coming up. It's switching. It's coming up like this. On the third interval, I'm decreasing and concave down. Decreasing and concave down are going to look like that. Kind of sad. And then the very last section of this, the fourth portion, is decreasing and concave up. Okay, so what's going to wind up happening here on this right side is it's going to come down and level out. There is an inflection point here. The inflection point here has the coordinates square root of 2 over 2, comma, e to the negative 1/2. On the left side, there is a second inflection point with coordinates negative square root 2 over 2 e to the negative 1/2. So at this point, you now have a graph where you have both inflection points identified. You have identified a maximum point, and you have looked at the first and second derivative indicators for increasing, decreasing, or concave up, concave down on each of the 4 panels. Now, something really important to be mindful of is if you have a scenario, and I'm just making something up here, first derivative, and let's say we have some point, -2, +3, and second derivative, we have something here, oh, I don't know, it's 0. Okay, if the first derivative is positive, um, positive, and negative, that would mean it's increasing, increasing, decreasing. Down here, the second derivative might be less than 0, and over here, the second derivative would be greater than 0. Now notice that between the first and second derivatives, you have a segment to the left of -2. You have a segment between -2 and 0. You have a segment between 0 and 3, and then you have a segment to the right of 3. What you want to do is for each segment, so I'm going to look at the leftmost, it is increasing. That's what the first derivative says. Notice the second derivative here says that it's concave down over that whole interval and concave up to the right of 0. Okay, so you take the information from both up. This is going to be increasing and concave down. On the next interval, notice you're still greater than 0. So it's going to continue to be increasing and it's concave down because between 0 and 2, it's still concave down. On the third panel, it's going to be increasing, but it's now going to be concave up. And on the fourth interval, it's going to be, notice we're now decreasing. We're going to be decreasing and concave up. If this actually forms a graph or not, I don't know. But what we can do then is for each of these 4 segments, here's something increasing and concave down. Increasing and concave down would continue to go like this. Increasing and concave up would go like this. Decreasing and concave up would go like this. This is going to be a pretty crazy looking graph. But what you want to do is after you get your first and second derivative, you want to break it down into segments like this and look at what the first and second derivative are telling you on each segment. That will tell you the shape of the curve on that segment. Okay, and go from there on deciding which shape needs to go on that segment of the graph. Okay, so I've tried to provide you with several examples. Some of them get a little bit lengthy because the second derivative stuff gets ugly, like there. On quizzes and tests, I'll be careful not to give you anything where the second derivative gets that bad. But notice you can get solutions to these. You can go to Wolfram Alpha, you can do photo math or something or other like that. And you can get answers to them.